My talk is about Toeplitz operator in the classical n-weighted Bergman space. But some of the result, as we see, I mean, you find it in the literature, that some of the results are extended to other spaces, like I work here in the classical n-weighted Bergman space, so you take analytic functions on the disk that are square integrable. But some of the result about Toeplitz operator, they have been extended to other spaces like the upper half planes and the Hardy space. Actually, most of the question in the Hardy space are closed now. They solved everything. Okay, so this is our Bergman space. The word A here is just to say analytic. So it's L2 closed subspace. So the projection from L2 to the Bergman space is well defined. It is nice space. It has a kernel or producing kernel. And so this is how it works, the projections from what they call Bergman projection. And so we define our Toeplitz operator. So what you do here? Okay, so this is the so-called the symbol here, F. Okay, so you take the function in H is in your Bergman space. You multiply by the symbol F, and then what you do after, you compress your result by the projection. You don't want to leave the Bergman space, so you compress the result, okay? So that is the projection to stay in the Bergman space, and that will be our Toeplitz operator. Of course, the Toeplitz operator, if your symbol is bounded, the Toeplitz is bounded, but the boundedness of Toeplitz operator is still an open question. We don't have necessary and sufficient condition to say that the Toeplitz operator is bounded or not. So keep in mind, this is very important point, because there are n-bounded symbols, F, n-bounded function that generate bounded Toeplitz operator, Okay, so now for those Toeplitz operator, there are two major questions, really open question. The first question is what Leon were talking about, is the commutativity. So if I have a TF, commutativity in the sense of the composition. So you try to figure out what are the operators that commute with it, okay? And there is another question, which is when is the product of two Toeplitz operator, let's say, is equal to another Toeplitz operator? And at some point you will see that these two questions are somehow related to each other, okay, at some point. Okay. So this is what will be. I will be dealing now for this presentation. I will talk about this one here, and I will show you some formal result in chronological order so that you see why the people are moving from a case to another case, okay? Okay, so here is just, these are simple property about it, really from the definition here. There is no tricks here. And this is what you mentioned when you have the F, the symbol becomes an analytic bounded function, so it's just multiplication operator. So this is the kind of thing. Okay, so here is the commuting problem. So commuting for us is the set of all Toeplitz operator that commute with one given. So let's say I take this is my given Toeplitz operator, and I would like to characterize all the operators, Toeplitz operator. So TG that commute, those are all the operators that commute with my TF. Okay, now we have the answer in the following cases. We start now here. This is Louhichi and Axler, 1991. That was the PhD of Louhichi was the student of Axler, and during his PhD they did this result. They say we know if the function f and g are bounded harmonic function, then everything is clear for them. But it's strong condition. Both of them, they have to be bounded harmonic function. So this, for us, this is done case. If you are in this situation, we know how it works. Second one. Now, after the PhD, Louhichi moved to the university where Rao is, University of Toledo in Ohio. And he got a position there, and then they start working together. Rao, he was not working in Toeplitz operator. He was doing approximation theory. But he got interested in Toeplitz operator after Louhichi joined the University of Toledo. Okay, so in their paper they say, okay, if you take f to be a radial function, then I can characterize everything that commutes with it. And basically, radial commutes only with radial. That was their result. So if you have a f that is radial symbol, whatever is gonna commute with it has to be also radial function. Okay. But inside, you will see inside this paper, there are a lot of things that you can use and stuff. And in my PhD, I really started from here. So I start really pushing the result that they got here. Okay. Then the three of them, they got this paper together. They said if f is analytic function, bounded analytic, so basically if you have here tf is a multiplication operator, then everything is going to commute with it has to be also multiplication operator. So they are saying here the analytic commutes only with the analytic. So now those are the three cases here, and then after nothing came. You see, after this one, harmonic, both harmonic, one radial and one bounded analytic function. And then starting 2000, nothing. And so we move it to the so-called quasi-homogeneous stuff. And the quasi-homogeneous, if I go back, it's really the idea is from here, this guy here, from this paper here. So let's say, for example, I take this symbol, look, Zn Z bar M. And I write it using the polar coordinates, and so it's going to be exponential I n minus m theta r n plus m. And so you see this part is like where you have the argument, and this is like my radial function. And this is where it comes from this notion of what we introduced, the so-called quasi-homogeneous Toeplitz operator. So we say this is a quasi-homogeneous of degree p if it can be written exponential I p theta times the radial function. Exponential I p theta times the radial function. Exactly like this question here. And this question, by the way, I did the visiting position University of Toledo, and apparently Rao, he asked this to Chuchovic. He told him, when he saw what he did with Axler, he said both of them are bounded harmonic function. Rao asked Chuchovic, he told him, okay, if I take a symbol of this form here, can you characterize all the operator that's going to commute with it? So if he takes f of this form, he asked him, can you characterize all the Toeplitz that they are going to commute with it? And at that time, he did not know the answer. Okay, so this is how I start working on this kind of things. Okay, so this is quasi-homogeneous. Now, quasi-homogeneous turns out to be really very good symbols. And look why we study this kind of stuff. So first of all, you have this nice decomposition of the L2. So every function L2, what we call polar decomposition, that looks like Fourier series. So you can write it under this form. So you see the function inside there, they are quasi-homogeneous of degree k, and that is a radial function. Here, basically what we are doing here is we are identifying the open disk, because you are dealing with the radial function. We are identifying now the open disk to the interval 0, 1, because you are dealing with the radial function here. So those guys are radial, this like this one here, okay? And so what is the idea now? We wanna characterize those guys, the commutant of those quasi-homogeneous Toeplitz operator. And then our ultimate goal would be like, for example, if I know a lot of things about the quasi-homogeneous Toeplitz operator, can I go to a larger class of symbols like the one I'm putting here, L2? So basically, to be able to say something about general symbols, you go and study the quasi-homogeneous Toeplitz operator. Okay. Now, another thing, interesting things, those quasi-homogeneous Toeplitz operator, they act on the orthogonal basis of the Bergman space as a shift operator with a weight, shift operator. And you know, it's very pleasant to work with the shift operator. So it makes the calculation really, I mean, straightforward and not complicated. I mean, this is, here I'm just giving you an example. Take this guy to be, for example, positive, and let's see how it does act on this. This is a vector in the orthogonal basis. So you just compute here, this is the usual inner product in L2. And so here, this is the integral. You interchange now sum and integrals, and you obtain this kind of things. And so why it's shift operator? Now look, you started from Zn here, and then you have Zn plus k. The k, remember, it's what we call the order of the stuff. This is what you see here, okay? So it shifts from Zn to n plus k. And this is the weight. Now this weight here, for the people who are familiar, this looks like the Mellin transform. It is the Mellin transform, okay? This is why we call it's like acts like a shift operator with the holomorphic weight. Now this one is the Mellin transform. So this is the next slide. I'm gonna introduce the Mellin transform, and for us we're gonna do the Mellin transform of function defined in the disk. So outside of the disk, for us the function is zero. Okay, it has nothing. So it's just a function on the disk. So that is what we call the Mellin transform. Mellin transform is known to be bounded on the right half plane, and it is holomorphic when real of z bigger than 2. Remember, I'm 2 because we are here in the measure RDR. Okay, that is the Lebesgue measure for us. In the disk, it's the normalized one. So it's R dr d theta divided by pi. So that the measure of the disk is 1. So that is why I said I wrote for this function, the one in L1 RDR. Okay, so I go back. So you see this one here. So this is your Mellin transform here. Okay, so this is what I wrote here. Now this is really the key for all the type of proofs that are involving the so-called quasi-homogeneous Toeplitz operator. So what you do here, you have one-to-one correspondence between the Toeplitz operator and a sequence of this Mellin. Okay, so this is the symbol here. So you have one-to-one correspondence between. So we don't basically, you just forget about the Toeplitz operator and you focus on this sequence of the Mellin transform, and you have one-to-one correspondence between them. Okay, now the results now that we obtain using this quasi-homogeneous Toeplitz operator is the following now. So you see this guy here, where is the pointer? This is the point. You see, so here you have a function that I wrote its polar decomposition. So everything there is Mellin, are quasi-homogeneous. And I say, let me see what's going to commute with this guy. So I have my function f, this one, is fixed. And I took it to be exponential I p theta phi. Okay? And I go and I check the Tg that commute with this guy. Now for the function g here, I write its polar decomposition. So I write this now, the g here is bound. I'm not putting any restriction on it. Okay, so just make sure the Tg has to be a bounded operator, but the G itself does not have to be bound. And I go and I check what's going to happen if you say that this guy commutes with this guy. The first part, which is the first result, tells you that it has to commute with each one inside. You see the exponential I p theta has to commute with each guy there. Now, the second part is important. The negative part has to be equal to 0. Basically, in the B here, what we are saying that quasi-homogeneous Toeplitz operator of opposite degrees, they don't commute with each other. So, for example, just an example. So, for example, if I have 2I theta phi, it cannot commute, for example, with something exponential minus 4I theta psi. Not possible. Because this positive, this is negative. They don't commute with each other. If they commute with each other, that means one of them must be equal to 0. So they commute only in the trivial case. So this is why we said the negative part here are 0. Okay. Now for the positive part, it is unique up to multiplication, up to a scalar, multiplication constant. So in the positive part here, you don't have a lot. That is, if it exists one, it has to be unique up to multiplication. Now, that is the first result with Lova. At that time, she was a PhD also of my advisor. So we were not happy with this. We were not satisfied with this one. We want to push a little bit this one. Okay, we want to see how do they look like, these guys here. Okay, we know that if they exist, they are unique up to a constant, but we want more. Okay, so this is what I did with Ralph. Okay. And now we found the following. If you have Toeplitz, they commute. You see, remember, we said that they commute with each, this guy commute with each one inside. So now, in the positive part, forget about the negative part, we focus on the positive part here. If they commute, their power must be connected to each other. The power are related to each other. So that was... So if these guys, they commute, if and only if the power are connected to each other. Now, the power here do not have to be Toeplitz operator. At this level, this guy here does not have to be Toeplitz operator. But if they commute, the power has to be connected to each other. Okay, now, but with Rao, we got this one. Now here, where the power is gonna be Toeplitz operator here. This is why I told you that this question here somehow related to this guy. So we are proving the following. Every time you have, if the Millin transform is a rational function in Z, that means polynomial divided by polynomial with the degree of the denominator strictly bigger than the degree of the numerator. So you have a rational function in Z, then you are sure about the existence of the so-called root of the Toeplitz operator. And here, root here, really, I mean, this is what I mean by a root. Okay? So if this guy, if the Millin transform of this guy is a rational function of Z, then you are sure that this will be a power of some Toeplitz operator of degree, quasi-homogeneous of degree 1. So you are sure that there exists psi, that you take it to power P is gonna give you this. Now that is good, because then everything that will commute with this will be sum of power of this. So if I write it here, sorry. So if your Toeplitz has a root, then, and if now you are saying this guy TG commutes with it, then the TG basically is just sum of powers of that root, nothing else. Sum of power of that root. And so you totally characterize the Toeplitz that they commute with this guy here. Okay, so this is what the meaning of this one here. Okay, now let's go to this question. Remember this part, this paper here. I told you in the beginning. Where is it? Ah, here. Okay, yeah. In this paper here, in the end, after they solve the problem, in the end they put a series, like I think three open questions. They put it in the end. The famous one of them is the following here. Okay, where is it? This one here. Okay, so they say if I take the function to be a harmonic function, the symbol, this guy, if this guy is harmonic, and if TG commutes with TF, then the G has to be a linear combination of F, constant times F plus D. That was their guessing, okay? That guessing is not true if you restrict yourself to, if you don't restrict yourself, sorry, to bounded symbol. So this is with Rao and Yusuf, so we choose this guy. You see, this one is harmonic, Z plus Z bar, very simple. It's the shift plus, it's adjoint, okay? S plus S star. And so now, this one, you will see it in most of the papers dealing with the quasi-homogeneous here, Toeplitz operator. Your symbol has to be truncated above. You don't have from minus infinity to plus infinity like the first result I showed to you. This one has to be truncated above, okay? So it's from minus infinity up to some capital N. N you want to be as big as you want, but you don't have from minus infinity to plus infinity. But truncated, so the what we call the polar decomposition here is truncated above by capital N. Okay, so if it's commute with it, then we are saying that the TG could be a polynomial of degree at most 3 in TF. So that means basically what I'm saying to you here, I'm saying to you that the squared and TZ plus Z bar cube are Toeplitz operator. So the power of these guys are Toeplitz operators. And so this this result showed that this here, you don't really need to have a linear combination. However, if you restrict yourself, you say, I want the symbol to be a bounded function, then yes, this guy will be a polynomial of degree 1 in TF, and you get exactly what they have here. You get exactly what they have here. And this is what, and this is what Trioli and Akaki, they did in 2017. This paper was before this one, but I'm writing the years as in Matsainet. This is the year of publication. This paper here has a reference. In its reference, he has this paper here. Okay, so Trioli and Akaki, they showed that if you take f to be here polynomial in Z, here an anti-analytic, so you have here harmonic function, and again you have the TG, but it has to be truncated above by capital N. And if you say the TG commutes with TF, then this guy will be a polynomial of degree at most 1 in F, so linear, like linear A times F plus B. Those are a constant. And here you see I wrote under certain extra condition. What I meant by certain, I did not want to bother you here with the technicality. These conditions that they put in this result here is to avoid these cases here, because they know that if you have this one or this one, then no, you can go up to a polynomial of degree 1, polynomial of degree 3 in Z plus Z bar, and the polynomial of degree at most 2 in Z plus Z bar squared. So they had to put extra condition to avoid those situation here. Okay, that is in their result. Okay, so now what we did recently, this is with Issa from Algeria, is to take sum of pair of quasi-homogeneous Toeplitz operators. So you have now 2, sum of 2, like this one. And I look and I go and try to find, okay, if this guys commute with this guy, so you have a pair, sum of pair, what can I say about this one? And it turns out the result tells you that if this commute with this guy, then first the M has to be equal to P. That M here has to be this P here. The L here has to be this S here. More than that, the whole Toeplitz operator, this guy, is just a constant times this guy. So basically, what commutes with the sum of a pair of quasi-homogeneous is the pair itself, nothing else. Okay? So that is the recent result. And I will finish by saying the following, which is about the bicommutant. That means the commutant of the commutant. This is the bicommutant. The terminology, we find it in Bourbaki. Bourbaki used this terminology, the bicommutant, the commutant of the commutant. They call the bicommutant. And so all the results that I showed you previously, all of them, they go in the direction of this conjecture. And the conjecture is only for the Bergman space of the unit disk, only in the Bergman space of the unit disk. The same result is not true if you go to the ball of Cn, okay? And this Vasilevsky, he mentioned this in one of his paper. He said that the conjecture, of course, is not true in the ball of Cn. And here it has, we are talking about the disk, unit disk, okay? And so basically what we are saying, if I'm gonna use here, I will use the terminology, the notation of Vladimir Muller. So the conjecture basically, it says the following. So if I use this notation of Vladimir Muller is using like a graph theory, the vertex are the vertex are Toeplitz operator. Let's say I have TF here, TG here, so those are the vertex, and TH, okay? And if we put edge between them, between the vertex, means they commute. So this guy, the conjecture tells you that if TH commute with TF, and the TG commutes with the TF, then we conjecture that the TH has to commute with the TF. So this is basically what is the conjecture is about. Okay, obviously, it's clearly none of them being the zero operator or the identity, to avoid those trivial cases. None of them being the identity or the zero operator. So all the result, I insist on that, all the result that you saw so far, they satisfy this conjecture here. They really they support this conjecture. They go in the direction of this conjecture. Okay, I'll stop here. Thank you very much.